Hello and welcome to Waka Breaking It Down. Today we're going to be looking at re-expressing data that is curved, but we want to straighten it out so we can use our linear regression tools. In the unit plan, you'll see that the feedback quiz should have already been kind of gone over. You should have read chapter 9, all about re-expression. You should have checked your answers to the feedback quiz. And I made a video already about the feedback quiz from chapter 9, explaining the solutions in there and kind of giving some insight to what's going on in this chapter. So that's probably the first thing you want to do before you come to this video is watch the video from the feedback quiz chapter 9. All right, once you have, then this video is just kind of going to be playing around with the data, some data sets. There's a practice worksheet list posted right here in the middle. You'll see right here. It looks like this when you open it up. It has the data here in lists, which you could just use to type into your TI Inspire. But it's going to be easier if you go to this TI Inspire dataset link here and you download the data set and then open it up on your TI Inspire on your laptop. It's going to be easier to work with, and quite honestly, you don't need to really have this on your handheld. It's very rare that a test question would ask you to plot all this data out and go through the full thing of re-expressing. Usually, they're just going to ask you questions about it or what you should do, and not really have you actually do it. Um, I mean, you need to be real familiar with it in order to answer those questions, though. So it's just going to be easier to work with on the TI Inspire on the laptop version instead of trying to do all this stuff on a handheld is really difficult. Well, it's just a little cumbersome, but you can do it. So if you can open up this data set here, you'll get this data set. It's got all kinds of data sets over here on the left. You'll see we've got 1, 2, 3, 4, 5, 6, like 6 different data sets here that we're not gonna do all of them, but we'll use a few of them. This really is the main lesson for this day in the unit plan. So watching this video is actually your lesson. It's not just a little extra practice or something. It's the lesson. So this is important that everybody watches and goes through. Okay, so just push pause if you need to get yourself ready. I'm going to get going on this TI Inspire data and this worksheet. Okay, here I go. So the first set is a pendulum, and we're swinging a pendulum back and forth. One of the physics things is that if the length of the pendulum gets longer, then the swing will get slower. It'll seem slower, like the number of swings that you can get in is slower. So that's what this is graphing out. All right, and then we're going to try to explain why isn't a linear model good? How can we re-express it and straighten it out and create an appropriate model, right? And then using that model to do some estimations. Okay, so let's take a look. Now we will be using this ladder of powers. That's the biggest thing. Well, let me back up one thing. Why do we have to straighten it in the first place? Why can't we just do regression? I know my calculator, I can just go in there and do like exponential regression or logarithm regression or any kind. I can do quadratic and cubics and all kinds of stuff. It'll do the regressions for me. So why do I have to straighten these things? Actually, your calculator is straightening the data first, making a linear equation out of it, and then turning it back into an exponential or a logarithm or something else. It's actually going through the same process that we're doing. That's how the calculator does these curve regression things. It'll straighten the data just like we are. The tools we have for inference with slope and all these inference tools we have only work if the data set you have is linear. These are linear tools. They're not made for curved data. So we have to straighten things out, and get it straight before we can use those tools. So the ladder of power allows us to do that. When you graph stuff out that's not straight, it's going to have one of these 4 shapes. It's either going to be curved like this, like this, like this, or like this, right? When you try to plot it out on a scatter plot. If let's say it looks like this, what we're going to do is we have options. We can either go down in the powers on the x variable, or we can go up in the powers on the y variable. quite often we choose to go down first and try that. Like in this case, I would probably do the logarithm of x if I had data that looked like this. By going up and down, what do we mean? Let me back up here. We're actually just talking about the power you put on your variable. So your original variable, just x or y, doesn't have anything done to it. It's just x or y. But if you go down the ladder, you could be doing the square root of x, or maybe the square root of y. I could do the cube root or any other root. Oftentimes we go all the way down to logarithm first. A logarithm is like a 0 power. So you could have a half as a power, 1/3 as a power, or we can go all the way to 0. You could even go negative, which will give you an inverse, right? Give you 1 over the value. So quite often though, we use logs. It's very, very common to use a log. It does the job, and it's kind of easy to work with. So that's going down in powers. Going up in powers, we're just like it says, we're either going to square our variable or cube it or whatever. So I don't know. Often we try to square stuff, maybe square root stuff sometimes, and then but usually we'll try to log it. Now that I'm going to use the expression overcooking something. So let's say my data is curved. Maybe it looks like this, right? And I want to straighten that out. So I say, okay, I'm going to go down in the x's, and I use a logarithm. So let's say I do that, but then when I get done with that, my data starts to look like this now. So you can see I had kind of a concave down, and now I have a concave up. I would call that overcooking it. You over straighten it. Like it started to get a little more straight, and then it got straight, and then you went so far that it actually started curving the other way. I call that overcooking it. So I went too far down in my ladder. Maybe I shouldn't have gone all the way to log. I should back up a little bit and just maybe try the square root instead of trying all the way down to a logarithm. And maybe that'll keep it straight and not overcook it and bend it the other way. All right, so I'm going to say that term overcooking. All right, so let's get to it. Let's just try some sets. That's how you learn. Excuse me. So pendulum data set. If you look here, it looks like it's the second data set in my TI-Nspire. Let's just plot it out, take a look at it. So I'm going to do a data and statistics page. And we're going to do the length as the explanatory variable and the number of swings as the response. And we can see it's curved, right? This is kind of that bottom left-hand corner of my circle. Oh, my computer's not happy. Okay, so we're on this bottom left-hand corner of the circle, which means I should probably try to go down in the X first. If that doesn't work, I can go down in the Y. Maybe I do both, right? It's possible. So what does going down means? Well, like I said, I'm going to try the logarithm first. So let's try that. So in my list, I'm going to try to do the logarithm. Well, sorry, whoops, wrong list. First of all, like, why is this not a good linear fit, right? Maybe I should talk about that first. So let me put a linear regression on this. Boom. I can see, like, this is what you need to be able to talk about in a test, right? They'll give you something like this. They'll most likely give you something like a residual plot. And they'll say, why isn't this a good linear fit? And you'll have to describe it. So mostly you're just looking at the curve and the residuals, and that's what you want to say. You can say, there's a pattern in the residuals. I can see that that's curved. It's not uniformly spread around the 0 line in my residuals, right? It needs to be uniformly spread, or we say consistently or uniform spread in the residuals. It should look kind of randomly scattered in the residuals. But if it isn't, if I can see this pattern where I have some above and then some below and then some above again, that's a pattern, right? So I don't want a pattern in the residuals. I want it to be just nice and randomly scattered along here. So that's what you have to describe on a test, is being able to describe the residuals and say, look, there's a pattern going on here. So it's not linear, right? So how do we straighten it? Let's go back to the data set. We already talked about I should go down in the powers. So up here, I'm just going to say log of length. And be careful. You see how when I type in log, it recognizes that? Well, that's because it's a calculator function. So you can't just call something log. Can I call it log of? I'll call it log of length. Okay, and then I'm going to call this log of swings, maybe log swing. All right, and you don't have to type them in down here. You can write an equation for it and just say this equals log. The calculator recognizes log, and I will do and put the length equation. You see how it turns bold? That's how I know it recognizes the column. So it's going to do the log of all the values in the length column. Hit enter, and there you go. You can even see down here, this one's log, right? If I want to make sure it looks like a decimal in my equation, I could go like times 1 with a decimal in it, and that'll change everything to a decimal. One thing you'll notice when you type in log, it's automatically using base 10. That's pretty common, but it's important if you're going to undo something or when we're solving the equations, you need to know what base it is. Okay, so it's base 10. I'll hit enter again, and it changed everything to decimals for me. Not that it matters. It'll still plot properly. All right, same thing over here, equals log, parentheses, and let's put in number swing. Number swing, it's just SW. That turned bold as well, so now I know it's recognizing the column. I hit enter, and it's doing the log of all those values. It's a calculator, so it's going to try to simplify things and stuff like that. Don't even worry about it. It's gonna plot properly. So let's go here now. I'll leave that. Okay, let's put in a new data and statistics page. And now we want let's do just the X value. So the log of the length, right? That's the X variable. We had length on the explanatory before, but now we're going to change it to log of length. But let's just keep the regular old swings. So the number of swings. Let's not make that the logarithm, right? Because you don't want to overcook it. So let's see. Oh, that looks pretty straight, doesn't it? So just by doing the log of the lengths, I've been able to straighten this out. Let's put the regression on it, check the residuals just to be sure. So I put my regression on there. Let's show the residual plot, analyze residuals, show residual plot. And there you go. This looks very, you can still kind of see there's a little bit of a pattern going on, but it's like the residuals are so small that this is much better than what it was, right? Now I can try to change this axis. Let me see what happens if I change this number swing into log swing and see if that does anything else. Oh my goodness. Now that looks really good, doesn't it? It doesn't look overcooked or anything. You can see how this is nice and even. So let me go back just to compare. So just the regular number swing wasn't bad, but I could still kind of see like these are above the residual line, these are below the residual line, and then these are all above again. Well, not all of them. These are above again. So it still feels like there's a little bit of a pattern going on there. So I tried the log of y, the log of swing, and that really kind of straightened things out. Now my residuals look completely kind of randomized. They look kind of evenly scattered out, right? Below, above, below, above, below, above, below. Very evenly scattered. I would be very happy with this if I was doing a real analysis for it. Okay, so that I'd stop right there and be like, hey, log swing, log length worked well. I'll just use those. Now let's go back to the worksheet so you can see what I'm going to be talking about. Okay, so we explained it's not appropriate because of the residuals had a pattern. We re-expressed it using log of x and log of y both. That was the best way to do it. When they say create an appropriate model, what is it? Well, the model now, if you look here, like I have my equation, right? I have this 1.72 as my y-intercept. I have a negative 0.453 as my slope. And when you look at the equation, it just says x and y. But you have to realize that the x is now the log of the length, and the y is now the log of the swing. Oh, so that's a little different. We haven't really worked with that before. So that's what I want to kind of work with now. Let me. So when you write these things out, you would have to actually, like, I would have to write it in there as this is the log of the swing, right? And write this out. Sorry, this is slow for me to write. And that's my hat now, right? That's my predictor. I'm trying to predict like the equation is predicting this. It's not predicting swing anymore. It's predicting log swing. Whoops. I'm going to write it while I can see it. So I got the 1.72. I'll go back to the other page so it's clear. But I'm just writing it here. So I have 0.453. And then the x, it's not x anymore. It's log of the length. Log length. All right. Sorry, so slow. Okay, let me go back here and then you can read it. Okay, there it is. That's really messy. It looks like a second grader wrote it, but that's me. Okay, so this is my explanatory variable, and then my response is log swing. So you'll see down here it says let's make a prediction, estimate the number of swings for a pendulum with a 10-inch string. So I'm going to do 10 in for length. That's true, but it's not just 10 times 0.45 now. I have to do the log of 10. Then I have to multiply by the 0.45, right, and get a number. And then 1.72 minus that. And then over here, remember, this is base 10 for the log. So I'm going to have to roll the log. If you remember from algebra 2, you have to take 10 to this whole power over here, this whole power, to equal the swing, which would be my solution. Let me do all this on a calculator page. Might make it a little easier. So I'm going to insert a calculator page. So let's do I'll do it piece by piece just so you can see. I'll do the log of 10, right? And then, well, let me just type it out. It's easier. So I'm going to just go 1.72 minus 0.45. And let me get some more decimals on there. I want to get, so this is 1.72055. The reason I'm feeling it's important to put decimals on there is because when you work with logarithms, 0.453188, sorry, mid-sentence. When you work with logarithms, you're doing powers, right? So this is 10 to the power of something. When you're doing powers, the extra decimals can make a difference. So I like to just throw in all the decimals to make sure I'm being really accurate and not rounding things too much. So you can see I'm just calculating the right-hand side, but I do have that log in there, right? I have that log. That's important. Hey, I hit enter, I get some number. Okay, I get a number, 1.26. That's not the number of swings. That's the log base 10 of the number of swings equals that. So to roll my log, right, I have to go 10, and 10 to that power will then equal the number of swings. And that's rolling the log from algebra 2. Okay, so I'm just going to go 10 raised to, and this power, I'm just going to copy paste that down so I get all the decimals. And then that is my number of swings. That's my prediction, 18.5. 18.5. So you see it? That's how we would do all the predictions. The same thing. You have to be able to work with whatever you re-express your data as and undo it, right? You're undoing that re-expression. So doing the re-expression allows us to use a linear model. But once you get the linear model, you can use it with the re-expression in it as part of it to get your predictions. Okay, so if I had a length of 10, I forgot what this was, inches or whatever, then the pendulum would swing 18 and a half times. I think we're talking about inches, yeah, and then it's, yeah, it's a 20, how many swings it makes in 20 seconds, okay? Now we could do 48 as well. I want to double check and make sure that is not a extrapolation. So I can look here, but this is the log stuff, right? So maybe I want to go to the original and look at that. I'm going to undo all this stuff. So now that you've seen it. Okay, so this is my original graph, my original data. You can see 10, we made a prediction for 10. And if you follow that up, I'm not going to the line. I'm actually I'm just, let me get rid of the line actually. So if I look at 10, if I kind of look at that curve pattern, I'm expecting to have a prediction right around 19, maybe a little less, right? Well, that's what we got, doesn't it? Yeah, we got 18.5 for our prediction of, our prediction of 10. Okay, so it gives you predictions on the curve, but you had to go through a linear model to do it, if that makes sense, I hope. Right? You can't directly make your predictions on the graph, right? You can't, our linear model stuff doesn't work. Okay, so that's called re-expressing the data. And again, it's just one of those, like, we got problems, right? Maybe I have an outlier. What do I do? Well, you don't throw it away. You analyze two different ways if you have an outlier. What if I have fanning? Well, maybe you better re-express it. What if I have a split domain? Well, you should split the domain and get two different models. Well, what if my data is curved? Well, you should re-express it, right? So that's what we're doing. It's just solving problems that you might face when you get different kinds of data sets. Okay, so I think you've seen the main things. Oh, sorry, by the way, 48 is a extrapolation. If you looked here at my original data only goes to like 38. So, that's too far out. That would be extrapolation. I'm not really allowed to do that. So I would just say, sorry, this is extrapolation. I'm not going to, I mean, I can actually put it in the equation and get a number, but I would have very, very low confidence. And that's what it's talking about here in this next part, F. I have really high confidence with the 10, even though I could do a confidence interval for the prediction, which we've kind of looked at those a little bit. But I would have very low confidence with any kind of prediction at 48 because it's outside my domain. Okay, so we got other data sets, right? There's the baseball one, there's the shore and boat one, there's the alligator one. Let me just do the alligator one and I'll be done with the video. Because I want, not done with the video, but done with that part of the video. I do want to try some of these things down here. This is very important to be able to kind of solve and using data or using an equation that's already been re-expressed. You see how this is square root, this is logarithm, this is the cube root, right? This has the log on both sides like we just finished doing. You need to be able to solve those and make predictions. Little algebra 2 practice. So don't just stop the video right now and be like, oh, I've got it all, right? I am going to do one more data set with the alligator weights, and then I'm going to go do a couple of these problems and run through them. So if you're like, okay, I've got the data set thing down, maybe jump ahead in the video and look for the solution of these. But maybe you want to walk through the alligator weights with me just one more time and take a look at how we do this. Okay, so I'm looking at my data sets. I got all kinds of stuff that I can play around with and practice. Let's look at the alligator set. What's this one look like? Okay, so let's graph it out. I'll go a little faster now. We got the weight and the length. So we're going to use the length of the alligator to predict its weight. All right, so this is a bunch of alligators that they've got some data on. Why is this important? Well, because it's really hard to weigh an alligator, but it's much easier to get the length of an alligator. You can almost look at it and use tools and stuff to kind of get the length of an alligator, but you don't really have to pick it up or move it or put it on a scale, right? It's really hard to weigh it. So if I can just measure the length of an alligator and then automatically know what it weighs, then that's a good model, right? Okay, but this is curved. I can see it already, but what are you supposed to do? You're supposed to put in the regression first. You're supposed to look at a residual plot. And then you're supposed to talk about the residual plot. I can see that there's a pattern in the residuals. I start out above, then I go below, and then I go above again. That's a pattern in the residuals. It does not look evenly scattered. Okay, so you would just mention that. I need to re-express this. This is, if I look at the data set up here, right? I'm not looking at the residuals. I'm looking at up here. This is the bottom right-hand corner of my circle of my ladder of powers. So I have this part of my circle. That means I should either go up in the x direction, like x squared or x cubed, or I should go down in the y, which means like square root of y or the log of y. I like to start with logarithms, so I'm going to try the log of y and see what happens, and then we'll go from there. Maybe I have to go x squared, maybe. Let's take a look. Okay, so the log of y is what I want to do. So I want to do the log of the length, or sorry, the log of the weight. So I'm going to just type in log weight. I'm going to have this ready just in case, but I'm going to say square the length. And I'm just going to do it right now. It's pretty easy, right? You just calculate log of weight, because I'm supposed to go down in the y direction. And then I'm going to just square the length. So I'll go length. You see how it turns bold? And I'm going to square all those. Hit enter. So I've got that ready to go. Let's do another graph now. So insert data and statistics. I'm just going to do the length as it is for right now. And let's see if the log of weight straightens that out enough. All right, it looks pretty good. But we noticed, like last time when we did that other data set, the first time we did it, it looked pretty good on the scatter plot. But when we looked at the residuals, we could see that it was there's still a little bit of a curve left. So that's why the residual plot is so good. Okay, I have to get my equation on there first in order to be able to do residuals. But show my residual plot. Okay, I'm looking at it. Oh, look at that. That looks pretty good already. I don't even have to do anything more, I don't think. Now I am curious. So let's see, if I were to do the square of the length, would it get any better, or does it actually overcook and get worse? So let me try the square of the length. Oh, you see how that actually got worse now? Now I have a pattern going this way, right? You can kind of see it. So I have a pattern in the residuals going the other way now, concave down instead of concave up. So I overcooked it. I did too much re-expression. So I'm going to change the square length back to length. Notice how it's going to straighten out a little more. And let's go back to the other one so you can see if I just do regular old length or weight. Where's my weight? Okay, so watch how it'll curve concave up now. Where's my residuals? I lost my residuals. Let me try them again. I just turned it off and turned it back on. So, okay, so we have concave up here, right? What if I did square length only? What happens? Not enough, right? It's still concave up. But when I do that log of weight, boom. Oh my goodness. Oh, I thought this overcooked last time. Oh, look how big my residuals are. So my residuals are, the scale isn't good. Every time I change it, my residuals aren't really, I kind of have to redo it to get the calculator to redo it for me. Let me try it again. Okay, now I was just looking at the scale over here and it was way too big. I couldn't see what was going on. So now it's concave down now, right? So that was overcooking it. Let's go back to just regular length. And that's what I want. Okay, so my model is log weight equals 0.579929 plus 0.015381 times the length. So that's my model. But it's log weight. So how would I make a prediction? Let's say I want to predict a length of 100. Okay, I would just put 100 into this equation, calculate the right-hand side. All of this will just equal some number. On the left-hand side, I got log. So I'm going to have to roll the log, right? Remember, this is base 10. So I'm going to have to roll the log 10 to the 10 to this power, right? And that will equal my weight then. All right, we could try it out on something if we wanted. Let me put in a calculator page. This will be the last thing I do for this. Sorry. So we had 0.5799, 0.5799, 29 plus 0.015381, 0.015381. My old brain does that. 15381. Okay, I think I got it. And let's put in 100. We'll predict If I have the length of an alligator is 100, what's the weight we're going to predict, right? Okay, so I'll hit enter. I have to undo the log because remember it's log a weight. So undo the log and I get 131, whatever it is, kilos, pounds, I forget. I didn't look it up. All right, now this is the curved set or the straightened set. Let me go back to the original. So this is length and weight. So if I had let me get rid of this. I don't want that messing things up. So if I had an alligator with a length of 100, you can see if I kind of fall in pattern with this, my prediction should be right about here, right? This would be what I'd estimate, maybe a little less than 150, right? Well, that's what we got. We got 131. That's what the model would predict. 131, right? This is like 50, 100, so 130 is like right in here. Whoops. Right in here is like 130. So, yeah, that's kind of what I would predict, like 130-ish. But we don't have to estimate, right? We have a good point estimate as our prediction. Perfect. Okay. Let's move on to the last piece here. So hopefully it all makes sense. But what if it isn't log? I've shown you log now, but what if it isn't log? What if you have some models that have other things? Well, this is your algebra 2. I teach algebra 2 as well. You just need to go back and remind yourself of how to undo stuff, right? Yeah, for this first one, they say predict the um, cost of a 1500 inch or 1500 square inch screen, right? So this is what I'm putting in for size, right? And you just put that in. When I get that all done, this is a square root. How do you undo a square root? Well, you square both sides, right? We should know this from algebra 2. So that's what I would do, right? You just square both sides after you get your number. What about these? This is the log again. So we've already done one of those. I'm going to roll the log and do 10 raised to this power, right? And that would give me my answer after I put 23 in, of course, in for time. By the way, you're not really allowed to go backwards. I'm not allowed to put in a y value and estimate an x value. You're actually not allowed to do that. You're supposed to go back to your graph. I would have to switch the x and the y here, come up with a completely different model, and use that new model with the x and the y switched to make predictions going the other way. You're not allowed to go backwards. What if it's a cube root? Well, you just, whatever you put into over here, you just raise it to the third power, right? To get rid of your cube root. This is just algebra 2 stuff. But it is important to know how to do. So if you're having trouble like rolling the log or whatever. All right, so those should all be the same as what I just mentioned. The one thing I did want to show you, let me just use these two equations to show you, or I'll just do it in general. Um, this equation with the double log and this equation with the single log, and maybe this is more for the mathy people, right? If you're not a mathy person, then this isn't super important. You don't need to know this for AP stats, but it's kind of interesting. This has a double log on it. If you solve for the left-hand side, so like if I have I'm just going to call this y, okay? And I'm just going to call this x. So if I'm trying to solve for y, I have to roll the log on both sides. So I get y equals, I roll the log and I get 10 raised to the 0.72 power plus 0.61 log of x. Now, using your algebra skills, this addition can be broken up into multiplication with the tens. This is just algebra. So if you're like, what? It's just a algebra, not a trick, but an algebra rule that I'm using with exponents. I can do this. Remember, because you multiply exponents, right? If you have two bases that are the same. So I've separated them out into two base 10s, and now I have multiplication in between them, and the addition is gone. This 10 to the 0.72 is just some number. I'm going to call it a. This 0.61 can go up in the power. This is a logarithm rule, right? If you have the log times something, you can move it up in the power. So I'm going to move that 0.61 up here as a power of x. which this is gone now. This 0.61 is gone. Okay, that's just a logarithm rule from algebra. And now this is log base 10, right? So I have 10 raised to the log base 10 of x. Well, x to the power. This whole thing is inside the log now. These are inverses of each other. These are inverse functions. If you remember from algebra 2, 10 raised to something and log base 10, those are inverse functions. So these actually kind of cancel out, and you're left with x raised to the 0.61. Does this look familiar? It should. This is a power equation. It's like my a and b to the, well, the variables here. So this is a power, like if I had x squared or x cubed or x to the fourth, it'd be like a quadratic or a cubic or something, but it's 0.61 instead of a square or a cube. So this has been deduced from something that had two logs in it that was linear, right? So this is what your calculator is doing. Your calculator is saying, I'm going to take that curved data, I'm going to make it a straight line, and then I'm going to undo this using my algebra rules, and I'm going to turn it into a power equation. So if you have the log on both sides of a linear equation, it's really a power equation. And the power regression on your calculator will do the exact same thing. It should come out very similar to that. Very similar to what I just did. If you have only a log on the left-hand side and not the right, like you have a log on the y but not on the x, if you do that same algebra trick where I take the base 10 and I roll the log, right, and then I separate it out. I'm gonna do it really quick here. I go times 10 and I separate it out again, 0.018. I'm going to actually raise that to the x, because remember, like x, if you have a power of a power, those multiply. So 0.018 times x would give you this as the power. I did the separating the tens out because of the addition, right? This becomes a number like a, this becomes a number like b, and then my x is in the power. So if you do the little algebra trick, you've just turned this into an exponential equation, right? A times b to the x. This is like my principal starting amount, b is my rate, and then x is my time period, right? So you've just turned a linear equation into an exponential, and it all came from the fact that you had log on the y, right? So those are two kind of special cases, but they come up a lot, right? You saw already in our data sets that we had log of y, we use that, and we also use log of x, log of y quite a bit. So we have power equation and exponential equations. That's what those turn into. Anyway, that's enough. Practice solving, right? Making predictions. Practice the ladder of powers, making sure that you can recognize which way do I go and knowing what that means as far as which variable gets going, gets a power on it, or maybe gets a logarithm or a square root, okay? And then you have to be able to look at residuals and talk about those, and look at the equation and write the equation with logs and square roots in them now. All right, so practice away. Good luck.